look up. Not at the ceiling, not at the screen, but up. Beyond the roof over your head, beyond the thin blue veil of our atmosphere, and into the infinite black. What you are looking at is not just a scattering of distant lights. It is a structure so vast, so ancient, and so profoundly complex that for most of human history, we didn't even know we were inside it. We called it the Milky Way, a faint, ethereal band of light smeared across the night sky. A river of milk spilled by a goddess, a pathway for souls. We saw it, but we could not comprehend it. We were like a single, microscopic organism, born and living its entire life on the surface of a colossal, invisible sphere, trying to map the sphere's true size by only looking at the tiny patch of ground beneath its feet. For centuries, that was our cosmic predicament. We were trapped inside a spinning, 100,000 light-year-wide disk of stars, gas, and dust, and because we were inside it, we could not see the forest for the trees. Every star we saw was a neighbor, every nebula a local cloud. The sheer scale of our galactic home was a secret kept from us by our own location. It was the ultimate cosmic mystery. How big is the Milky Way? And if we can't even measure our own home, what hope do we have of measuring the universe? This question, this fundamental challenge to our cosmic perspective, is what drove generations of astronomers to the brink of madness and genius. It is a story of human ingenuity, of overcoming the limitations of our senses, and of a profound, almost spiritual shift in our understanding of reality. It is the story of how we finally, definitively, answered the question of our cosmic address. And if you are ready to take this journey with us, to peel back the layers of the universe and witness the true, mind-bending scale of our home, then take a moment right now to hit that like button and subscribe to Cosmo Depth. It's the best way to ensure you don't miss the next chapter in humanity's ongoing exploration of the deep cosmos. Your support helps us continue to bring these massive, in-depth stories to life. Now let's begin where all great journeys begin. At the beginning of the realization that we were lost, for the longest time, the universe was a cozy, manageable place. It was the realm of Ptolemy and Aristotle, a series of perfect crystalline spheres with the Earth, naturally, at the center. The stars were fixed points of light, pinned to the outermost sphere, and the Milky Way was just a smudge, a meteorological phenomenon, perhaps, or a celestial stain. This geocentric model, while elegant, was fundamentally flawed, but it served as the reigning cosmic truth for over 1,000 years. Then came the revolution. Copernicus moved the Earth, Kepler defined the orbits, and Galileo turned his crude telescope to the heavens. What he saw was a revelation. The Milky Way, that hazy band of light, was not a cloud or a stain. It was composed of innumerable stars, packed so tightly together that their individual lights blurred into a continuous glow. This was the first hint of the galaxy's true nature, the first crack in the crystalline sphere. But even with this knowledge, the scale remained elusive. The next major leap came from a man whose name is synonymous with the very act of mapping the cosmos, William Herschel. In the late 18th century, Herschel, with the help of his sister Caroline, undertook the monumental task of stargazing. Imagine trying to determine the size and shape of a vast, dark forest while standing inside it, blindfolded, and only being able to count the trees in a few directions. That was Herschel's challenge. He made a crucial, but ultimately flawed, assumption that all stars had roughly the same intrinsic brightness. If this were true, then a dimmer star must simply be farther away. By counting the number of stars in different directions and assuming a uniform distribution, he attempted to draw a map of the stellar system. His map, published in 1785, was a rough, flattened disk, a shape that we now know is broadly correct, but his measurements were wildly off. He placed the Sun near the center of this system, and he estimated the entire galaxy to be only about 5,000 light-years across. Why was he so wrong? The answer lay in the very thing that makes the Milky Way so beautiful: cosmic dust. Herschel's view was blocked. The vast, opaque clouds of dust and gas that fill the galactic plane, the same clouds that give birth to new stars, acted like a thick, interstellar fog. He could only see a small, local bubble of stars, and he mistook that bubble for the entire universe. His map was not of the Milky Way, but of the local stellar neighborhood. The true, immense size of the galaxy remained hidden behind a curtain of cosmic soot. This was the state of affairs at the dawn of the 20th century. Astronomers knew the Milky Way was a disk of stars, and they knew the Sun was somewhere in it, but they had no reliable way to measure the distance to the far side of the galaxy, let alone its true diameter. The universe was still, in a sense, a small, provincial place, with our Sun comfortably near the center. The stage was set for a radical re-evaluation, a cosmic eviction notice that would finally force humanity to accept its true, peripheral place in the grand scheme of things. The key to unlocking the galaxy's true dimensions would not come from counting stars, but from studying a peculiar, pulsating type of star that acted as a cosmic yardstick. Enter Henrietta Swan Leavitt. Working at the Harvard College Observatory in the early 1900s, Leavitt was part of a team of women, often referred to as computers, who analyzed photographic plates of the night sky. Her focus was on the Magellanic Clouds, two small, irregular galaxies orbiting the Milky Way. Within these clouds, she studied a class of stars known as Cepheid variables. These stars don't shine with a steady light. They brighten and dim in a regular, predictable cycle. What Leavitt discovered was one of the most profound relationships in all of astronomy: a direct correlation between a Cepheid's period of pulsation, how long it takes to go from bright to dim and back again, and its intrinsic luminosity, its true, absolute brightness. The longer the period, the brighter the star. Think of it like this. Imagine you have a set of light bulbs, all of which are the same brand and wattage. If you see one that looks dim, you know it's far away. But what if you had a set of light bulbs where the brighter the bulb, the slower it flickered? Leavitt had found the flicker rate that told astronomers the true wattage of the star. Since all the Cepheids in the Magellanic Clouds were roughly the same distance from Earth, Leavitt could compare their apparent brightness to their true brightness, derived from their period, and establish a period luminosity relationship. This was the cosmic yardstick. Once astronomers calibrated this relationship using nearby Cepheids, whose distances could be measured by other means, they could look at any Cepheid, measure its period, know its true brightness, compare that to its apparent brightness, and calculate its distance with unprecedented accuracy. The stage was now set for the man who would use this new tool to redraw the map of the universe: Harlow Shapley. Shapley, a brilliant and ambitious young astronomer working at the Mount Wilson Observatory, took Leavitt's discovery and applied it to a different set of celestial objects: globular clusters. These are ancient, dense, spherical collections of hundreds of thousands of stars orbiting the Milky Way in a vast, spherical halo. Shapley realized that these clusters were the key to seeing beyond the dust veil that had fooled Herschel. The globular clusters, unlike the stars in the galactic disk, were mostly located above and below the dusty plain of the Milky Way. They were outside the fog. By measuring the distance to the Cepheid variables within these clusters, Shapley could map their three-dimensional distribution. The results were nothing short of revolutionary. In 1917, Shapley published his findings. He found that the globular clusters were not centered on the Sun, as Herschel had thought. Instead, they formed a vast spherical distribution centered on a point thousands of light years away, in the direction of the constellation Sagittarius. This point, Shapley correctly deduced, was the true center of the Milky Way galaxy. The implications were staggering. First, it meant that the Sun and the Earth were not at the center of the universe, or even the center of our own galaxy. We were relegated to the suburbs, a position about 30,000 light years from the galactic core. This was the second great demotion in human history, following Copernicus's removal of Earth from the center of the solar system. Second, and most importantly for our question, Shapley's map revealed a galaxy of truly colossal proportions. Based on his measurements, he estimated the diameter of the Milky Way to be an astonishing 300,000 light-years across. This was 60 times larger than Herschel's estimate and far larger than any astronomer had previously conceived. The universe, or at least our galaxy, had just become unimaginably vast. Shapley's estimate, while closer to the truth than any before it, was still too large. He had made a slight error in his calibration of the Cepheid period luminosity relationship, but the fundamental breakthrough, the realization of the galaxy's immense size and our peripheral location, was correct. The Milky Way was no longer a small, local star system. It was a giant, island universe. But the story of the Milky Way's size doesn't end with Shapley. In fact, his work immediately ignited one of the most famous and consequential debates in the history of science. The Great Debate of 1920. The debate pitted Shapley against Heber Curtis. The core question was simple, yet world-altering. Was the Milky Way the entire universe, or were the faint spiral-shaped nebulae scattered across the sky actually separate galaxies, or island universes, far outside the bounds of our own? Shapley argued for the former. He believed the Milky Way was the whole show, a single, enormous galaxy, and that the spiral nebulae were merely clouds of gas and dust within it. His colossal estimate of the Milky Way's size supported this view. If the Milky Way was 300,000 light-years across, there simply wasn't room for other galaxies. Curtis argued for the latter. He believed the spiral nebulae, like the Andromeda Nebula, were independent galaxies, each comparable in size to our own, and located millions of light-years away. He pointed to the observation of novae, exploding stars, in these nebulae, which seemed to be too faint to be inside our galaxy. The debate was a draw, a stalemate of compelling but incomplete evidence. The true answer would require a telescope more powerful than any before it, and a new, definitive measurement of distance. The man who would settle the great debate and, in doing so, shrink Shapley's galaxy while simultaneously expanding the entire universe, was Edwin Hubble. Hubble, working with the newly completed 100-inch Hooker telescope at Mount Wilson, the most powerful telescope in the world at the time, focused his attention on the Andromeda Nebula. In 1923, he began searching for Cepheid variables within it. It was a painstaking, meticulous process, but he found them. Using Leavitt's period luminosity relationship, Hubble calculated the distance to the Andromeda Nebula. His result was stunning. Andromeda was not a local gas cloud. It was 900,000 light-years away, a number he would later revise to over 2 million. This distance placed it unequivocally outside the bounds of Shapley's colossal Milky Way. The universe was instantly and irrevocably transformed. The Milky Way was no longer the universe, it was just one galaxy among billions. Curtis was right about the island universes, and Shapley's estimate of the Milky Way's size, while a massive step forward, was now seen in a new context. With the universe now known to be filled with other galaxies, astronomers could refine the measurement of our own. By the mid-20th century, the accepted size of the Milky Way's visible disk had settled to approximately 100,000 light-years in diameter, with a thickness of about 1,000 light-years. This is the number that has been taught in schools for decades, the number that defines the vast, beautiful spiral we imagine ourselves to be in. But this number, 100,000 light-years, is only the size of the visible disk. It is the size of the city lights, the part we can see. It is not the size of the entire galactic territory. To truly answer the question, how big is the Milky Way? We must look beyond the light, beyond the stars, and into the invisible, colossal structure that truly defines our galaxy's boundary. We must talk about dark matter. Imagine a cosmic merry-go-round. On a normal merry-go-round, the horses on the outside must travel faster than the horses on the inside to complete a rotation in the same amount of time. But in a galaxy, the physics are different. The stars are held in orbit by the gravitational pull of all the mass inside their orbit. If all the mass were concentrated in the center, the stars on the outside would move slower, just like the outer planets in our solar system move slower than the inner ones. But when astronomers began to measure the rotational speed of stars in the Milky Way and in other spiral galaxies, they found something deeply unsettling. The stars on the outer edges were orbiting just as fast, or even faster, than the stars closer to the center. The galaxy was spinning like a solid disk, not like a solar system. This observation, first systematically studied by astronomer Vera Rubin in the 1970s, was a profound violation of Newtonian physics, unless there was a massive amount of unseen matter providing the extra gravitational pull. The visible stars, gas, and dust simply did not contain enough mass to hold the outer stars in such fast orbits. This missing mass, this invisible gravitational scaffolding, was dubbed dark matter. And it is dark matter that defines the true, colossal size of the Milky Way. The visible disk of stars is merely a small, luminous island floating within a gigantic spherical cloud of this mysterious substance. This cloud is called the dark matter halo. The dark matter halo is the true gravitational boundary of our galaxy. It is the structure that dictates the orbits of the stars, the motion of the satellite galaxies, and the ultimate extent of the Milky Way's influence. The visible disk, the 100,000 light-year wide spiral, is only the tip of the iceberg. So, how big is this invisible halo? How far does the Milky Way's gravitational dominion truly extend? The answer is a number that dwarfs Shapley's original estimate and makes the 100,000 light-year disk seem almost insignificant. Modern measurements, which rely on tracking the motion of distant globular clusters, satellite galaxies, and streams of stars that have been torn from those satellites, suggest that the dark matter halo of the Milky Way extends out to a radius of at least 190 kiloparsecs, or about 620,000 light-years. This means the true diameter of the Milky Way is approximately 1.24 million light-years. Let that sink in. The galaxy we thought was 100,000 light-years across is, in its full gravitational extent, over 12 times larger. This is the first part of the answer to our question. The Milky Way is not just a spiral disk, it is a dark matter colossus. But the story is far from over. To truly appreciate this scale, we must dive deeper into the nature of this dark halo, understand the cosmic forces that shaped it, and explore the latest, most cutting-edge discoveries that are pushing the boundary even further out. We must understand the cosmic web, the galactic cannibalism that built our home, and the cosmic void we may be traveling through. The journey continues as we explore the invisible architecture of the cosmos. The dark matter halo is not just a theoretical construct, it is the gravitational skeleton of the Milky Way. Without it, our galaxy would have spun itself apart billions of years ago. The fact that the stars in the disk are moving so fast yet remain bound is the most compelling evidence for its existence. But what exactly is it? The prevailing theory is that dark matter is composed of a new, exotic type of particle that interacts with normal matter only through gravity. It doesn't emit, absorb, or reflect light, which is why it is dark. It simply provides the necessary mass. The distribution of this dark matter is not uniform. Simulations suggest that the halo is clumpy, filled with smaller, dense pockets of dark matter called subhalos. These subhalos are the gravitational remnants of smaller dwarf galaxies that the Milky Way has consumed over billions of years. This process of galactic cannibalism is a crucial part of the Milky Way's history and its current size. Our galaxy didn't just form in isolation. It grew by relentlessly absorbing smaller neighbors. When a dwarf galaxy falls into the Milky Way's gravitational well, the immense tidal forces of the larger galaxy begin to tear it apart. The stars and gas from the dwarf are stretched into long, arcing streams that wrap around the Milky Way, like ribbons of stellar debris. These stellar streams are one of the most powerful tools astronomers have for mapping the true extent of the dark matter halo. By tracking the orbits of these streams, scientists can measure the gravitational field of the Milky Way far beyond the visible disk. The farther out a stream is found, the farther out the gravitational influence, and thus the dark matter halo, must extend. One of the most famous examples is the Sagittarius dwarf spheroidal galaxy. Over the last few billion years, this small galaxy has been slowly shredded by the Milky Way's gravity, leaving behind a massive, looping stream of stars that encircles our galaxy multiple times. The sheer size of this stream and the gravitational force required to maintain its orbit confirms the colossal mass and extent of the dark halo. Another recent discovery that has pushed the boundary even further is the Virgo stellar stream. This stream, which is thought to be the remnant of another devoured dwarf galaxy, extends out to distances of over 100 kiloparsecs, 326,000 light-years from the galactic center. The existence of these streams at such extreme distances is definitive proof that the Milky Way's gravitational influence is far more extensive than the visible disk suggests. The latest research, which you can find in the most recent astrophysical journals, is constantly refining the size of this halo. A 2020 study, for instance, used the velocity of the Milky Way's satellite galaxies to predict the edge of the dark matter halo to be around 292 kiloparsecs in radius, or about 952,000 light-years. This would put the full diameter of the Milky Way at nearly 2 million light-years. Why the difference in estimates? Because the edge of the dark matter halo is not a sharp, defined line. It is a fuzzy boundary, a point where the gravitational influence of the Milky Way finally gives way to the gravitational influence of the surrounding cosmic environment. It is the point where the galaxy's rotation curve finally begins to drop off. This brings us to the next layer of complexity. The Milky Way's place in the local group, our galaxy, is not alone. It is part of a small collection of galaxies called the local group, which is dominated by two giants, the Milky Way and the Andromeda Galaxy, M31. Andromeda is even larger than the Milky Way, with a visible disk of about 220,000 light-years and a dark matter halo that is also colossal. The two galaxies are currently about 2.5 million light-years apart, but they are hurtling toward each other at a speed of about 110 kilometers per second. This is not a gentle drift. It is a gravitational embrace that will culminate in a spectacular collision in about 4.5 billion years. The gravitational interaction between the Milky Way and Andromeda is already a factor in defining the outer limits of our galaxy. The two dark matter halos are beginning to feel each other's pull, and the space between them is not empty. It is filled with the gravitational tension of two cosmic titans on a collision course. The collision itself will not be a head-on crash of stars. The distances between stars are so vast that very few, if any, will actually collide. Instead, the two galaxies will pass through each other, their immense gravitational fields stirring and reshaping the stellar disks. Over the course of 1 billion years, they will merge to form a new, larger, elliptical galaxy that astronomers have affectionately nicknamed Milkomeda. The size of Milkomeda will be the ultimate final size of our galactic home, a structure that will dwarf the current Milky Way. But even now, the gravitational influence of Andromeda is part of the Milky Way's extended domain. But the local group is itself part of an even larger structure, the Virgo supercluster. The universe is not a random scattering of galaxies. It is organized into a vast, intricate network known as the cosmic web. Galaxies cluster into groups, groups cluster into clusters, and clusters cluster into superclusters, which are the largest known structures in the universe. These superclusters are separated by immense, empty regions called voids. The Milky Way and the local group are located on the outskirts of the Virgo supercluster, a massive collection of over 1,000 galaxy groups centered on the Virgo cluster, which is about 54 million light-years away. The entire Virgo supercluster is about 110 million light-years across. However, in 2014, a team of astronomers discovered that the Virgo supercluster is just a small appendage of an even more enormous, previously unrecognized supercluster that they named Laniakea, which means immense heaven in Hawaiian. Laniakea is a truly mind-boggling structure. It contains about 100,000 galaxies and stretches over 520 million light-years across. The Milky Way is located near the edge of this supercluster, and all the galaxies within Laniakea are flowing toward a single, massive gravitational center called the Great Attractor. The Great Attractor is a diffuse concentration of mass, a gravitational anomaly that is pulling the Milky Way, Andromeda, and all the other galaxies in Laniakea toward it at a speed of hundreds of kilometers per second. This flow, this cosmic current, is the ultimate expression of the Milky Way's motion through the universe. So, when we ask, how big is the Milky Way? The answer has 3 layers. The visible disk, approximately 100,000 light-years in diameter. This is the luminous part, the spiral arms, the stars we can see. The dark matter halo, approximately 1.2 to 2 million light-years in diameter. This is the gravitational extent, the true boundary of the galaxy's mass and influence. The cosmic context. The Milky Way is a component of the local group, which is part of the Laniakea supercluster, a structure over 500 million light-years across. Our galaxy's motion is dictated by the gravitational forces of this immense cosmic web. The final, definitive size of the Milky Way is the size of its dark matter halo, the invisible giant that contains the visible spiral. It is a structure that is constantly being redefined by new observations and new physics. But the story of the Milky Way's size is not just about numbers. It is about the nature of reality itself. It is about the fact that 95% of the mass that defines our home is invisible, a ghost in the machine that we can only detect through its gravitational pull. To truly grasp the implications of this colossal, invisible home, we must now turn our attention to the microscopic details that make up the vastness. We must explore the galactic center, the supermassive black hole that anchors the entire structure, and the cosmic forces that are constantly reshaping the galaxy's arms. The journey into the depths of the Milky Way continues. The immense scale of the Milky Way, defined by its dark matter halo, forces us to confront the sheer emptiness of space. If the galaxy is over 1 million light-years across, and the visible disk is only 1/10 of that, then the vast majority of our home is a void, a gravitational field with almost nothing in it. To understand this emptiness, we must first understand the architecture of the visible disk. The 100,000 light-year spiral is not a uniform structure. It is a delicate, dynamic system composed of several distinct components: the central bulge, the disk, the halo, and the spiral arms. The central bulge is a dense, football-shaped region at the very heart of the galaxy. It is packed with old red stars, and it is the oldest part of the Milky Way. The density of stars here is staggering, thousands of times greater than in our solar neighborhood. If we lived in the bulge, the night sky would be a continuous, blinding spectacle of light. At the very center of this bulge lies the gravitational anchor of the entire galaxy, Sagittarius A, SGRA, a supermassive black hole with a mass of over 4 million times that of our Sun. This black hole is the engine of the galactic core, a silent, invisible behemoth whose gravity dictates the orbits of stars for thousands of light-years around it. The discovery of Sub A was a triumph of modern astronomy, requiring decades of meticulous observation of the orbits of stars near the galactic center. Astronomers tracked the motion of a star named S2, which orbits SGRA in a tight elliptical path, completing a full orbit in just 16 years. The speed and tightness of this orbit could only be explained by the presence of an immense, compact mass, a black hole. The influence of SGRA is profound. While it doesn't suck in the entire galaxy, its gravity is the ultimate reference point for all motion within the Milky Way. The entire 100,000 light-year disk spins around this central point. Surrounding the bulge is the disk, the flattened, rotating structure that contains the spiral arms. This is where the majority of the galaxy's young, blue stars, gas, and dust reside. Our own Sun is located in the disk, about 27,000 light-years from the galactic center, in a minor arm called the Orion Arm, or sometimes the local spur. The spiral arms themselves are one of the most beautiful and misunderstood features of the Milky Way. They are not rigid physical structures, but rather density waves, like a traffic jam on a highway. As stars and gas orbit the galactic center, they periodically encounter these density waves. When they enter a wave, they slow down. The density of matter increases, and this compression triggers the collapse of gas clouds and the birth of new, bright, blue stars. The spiral arms are therefore defined by their youth and brightness. The blue, massive stars that are born in the arms burn out quickly, so they never make it far from their birthplace. The older, redder stars pass through the arms, slow down, and then continue their orbit, largely unaffected. The spiral pattern is constantly being refreshed, a transient feature of the galaxy's rotation. The four major spiral arms of the Milky Way are the Perseus Arm, the Scutum Centaurus Arm, the Norma Arm, and the Outer Arm. Our Sun is nestled between the Perseus and Scutum Centaurus arms. Above and below the disk is the stellar halo, a vast, spherical region that is sparsely populated with very old, metal-poor stars and the aforementioned globular clusters. This is the realm that Shapley first mapped, and it is the visible component that extends farthest from the galactic center. The stars in the stellar halo have highly elliptical, random orbits, unlike the orderly, circular orbits of the stars in the disk. They are the oldest inhabitants of the galaxy, relics from a time when the Milky Way was still forming. Many of these stars, and the globular clusters they belong to, are the skeletal remains of dwarf galaxies that were consumed by the Milky Way billions of years ago. This is where the visible galaxy, the 100,000 light-year disk, transitions into the invisible dark matter halo. The stellar halo is the gravitational buffer between the luminous core and the dark, colossal boundary. The existence of these distinct stellar populations, the young, metal-rich stars of the disk and the old metal-poor stars of the halo, tells a story of galactic evolution. The disk formed later from gas and dust that had been enriched by the supernovae of earlier generations of stars. The halo formed first, from the pristine, primordial gas of the early universe. The size of the Milky Way, therefore, is a measure of its age and its history of violence. Every time the galaxy consumed a smaller neighbor, it added mass to its dark matter halo and scattered a new stream of stars into its stellar halo. The galaxy grew by accretion, like a cosmic snowball rolling through the early universe. The most recent and compelling evidence for this violent past comes from the discovery of the Gaia Enceladus/sausage GES structure. In 2018, data from the Gaia Space Telescope, which is meticulously mapping the positions and motions of billions of stars in the Milky Way, revealed a massive, ancient merger event. Astronomers found a large population of stars in the stellar halo that were all moving in highly eccentric, sausage-shaped orbits. These stars were moving in a coordinated, chaotic way that was completely different from the rest of the halo. The only explanation was that these stars were the remnants of a single, massive dwarf galaxy that collided with the Milky Way about 10 billion years ago. This dwarf galaxy, which was about the size of the Small Magellanic Cloud, was completely torn apart by the collision, its stars scattered into the halo, and its dark matter contributing significantly to the Milky Way's dark matter halo. This event, the Gaia-Enceladus merger, was a defining moment in the Milky Way's history. It was the last major merger event, and it is believed to be responsible for heating up the Milky Way's original disk, thickening it, and creating the distinct thick disk component we see today. The size of the Milky Way, then, is a direct consequence of this ancient, violent history. The dark matter halo, which defines the galaxy's true size, is a fossil record of all the smaller galaxies the Milky Way has consumed. The farther out the halo extends, the more mass it contains, and the more gravitational influence it exerts. But the Milky Way is not just a collection of stars and dark matter. It is a dynamic, living system, constantly interacting with its environment. And its environment is not empty. The Milky Way is currently being orbited by a host of satellite galaxies, the largest of which are the Large Magellanic Cloud, LMC, and the Small Magellanic Cloud, SMC. These are the largest surviving remnants of the Milky Way's cannibalistic past. The Large Magellanic Cloud is a dwarf galaxy about 160,000 light-years away. It is a massive satellite, about 10% the mass of the Milky Way, and it is currently on its first close pass around our galaxy. The gravitational interaction between the LMC and the Milky Way is so strong that it is having a profound effect on our galaxy's structure. The LMC is so massive that its gravity is tugging on the Milky Way's disk, causing it to warp and oscillate. It is also creating a massive stream of gas that is being pulled from the LMC and is currently falling into the Milky Way. This gas will eventually fuel a new burst of star formation in our galaxy. More importantly for our question of size, the LMC's gravity is also perturbing the dark matter halo. The LMC is so massive that it is dragging a massive wake of dark matter behind it as it orbits the Milky Way. This wake is causing the dark matter halo to become lopsided and non-spherical. This discovery, confirmed by the Gaia data, means that the Milky Way's dark matter halo is not the smooth, perfectly spherical structure that simulations once predicted. It is warped, lopsided, and dynamic, a testament to the ongoing gravitational battle with its largest satellite. This dynamic interaction is what is constantly redefining the Milky Way's size and mass. The mass of the LMC is so significant that it has forced astronomers to re-evaluate the total mass of the Milky Way itself. The most recent estimates, taking the LMC's influence into account, place the total mass of the Milky Way, including the dark matter halo, at around 1.5 trillion solar masses. This mass is the ultimate determinant of the galaxy's size. The more mass a galaxy has, the farther out its gravitational influence extends, and the larger its dark matter halo must be. The Milky Way, therefore, is a gravitational giant, a colossal structure whose true size is dictated by the invisible, mysterious substance that makes up the vast majority of its mass. But the story of the Milky Way's size has one final, mind-bending twist, a twist that takes us from the colossal to the truly incomprehensible, the KBC void. The universe, as we established, is structured like a cosmic web, with galaxies clustered into superclusters and separated by voids. For a long time, astronomers assumed that the Milky Way was located in a relatively average, dense part of the cosmic web. However, in 2013, a team of astronomers discovered that the Milky Way is actually located near the edge of a vast, empty region of space called the KBC void, named after the three astronomers who discovered it: Keenan, Barger, and Cowie. The KBC void is the largest known void in the universe. It is a spherical region of space that is over 1 billion light-years in diameter, and it is almost completely empty of galaxies. The density of galaxies inside the void is about 20% lower than the average density of the universe. The Milky Way, the Local Group, and even the Virgo supercluster are all located near the edge of this immense void. We are living in the cosmic suburbs of a supervoid. The existence of the KBC void has profound implications for the Milky Way's motion. The galaxies on the far side of the void are pulling us away from the void's center, contributing to the overall flow of the Laniakea supercluster toward the Great Attractor. This means that the Milky Way's motion through space is not just a simple orbit around the galactic center. It is a complex, multi-layered journey dictated by the gravitational forces of structures that are hundreds of millions of light-years away. The question, how big is the Milky Way, has evolved from a simple measurement of a disk of stars to a profound inquiry into the nature of mass, gravity, and the structure of the universe itself. The answer is not a single number, but a hierarchy of scales. The luminous core, 100,000 light-years. The gravitational boundary, dark matter halo, 1.2 to 2 million light-years. The cosmic context, Laniakea supercluster, 520 million light-years. We finally know how big the Milky Way is, not because we can see its edge, but because we have learned to read the invisible language of gravity. We have learned to map the ghost in the machine, the dark matter that defines our home and dictates our fate. But the story of the Milky Way's size is still being written. Every new telescope, every new dataset, pushes the boundary a little further out, revealing a galaxy that is more massive, more dynamic, and more mysterious than we ever imagined. The next chapter in this cosmic saga is about the future of the Milky Way. What happens when two colossal dark matter halos finally collide? What will the ultimate size of our galactic home be? The collision between the Milky Way and Andromeda, the event that will create Milkomeda, is the ultimate conclusion to the story of our galaxy's size. When the two galaxies finally merge, the resulting elliptical galaxy will be a true giant, a structure that will dwarf the current Milky Way. The merger will take place over hundreds of millions of years, a slow, gravitational dance that will eventually settle into a new, stable configuration. The dark matter halos of the two galaxies will merge first, creating a single, even more massive halo that will extend out to a radius of several million light-years. The stars and gas of the two disks will be violently stirred, eventually settling into a smooth, elliptical shape. The size of Milkomeda will be the final, definitive answer to the question of our galactic home's size. It will be a galaxy of truly colossal proportions, a testament to the power of gravity and the relentless process of cosmic evolution. But until then, we live in a galaxy that is defined by its invisibility. We are a luminous speck in a colossal, dark ocean. And the journey to understand that ocean, to map its currents and its boundaries, is the greatest adventure humanity has ever undertaken. The realization that the Milky Way is defined by its invisible dark matter halo, a structure extending over 1 million light-years, fundamentally changes our relationship with the cosmos. It shifts the focus from the visible, star-filled beauty of the spiral arms to the silent, gravitational scaffolding that holds it all together. To truly appreciate this scale, we must now delve into the tools and techniques that allowed us to measure the unmeasurable, to weigh the invisible. The entire history of determining the Milky Way's size is a history of finding cosmic distance ladders. Each rung on this ladder allowed us to look farther out, past the limitations of the previous method. The first rung was parallax, the apparent shift in a star's position as the Earth orbits the Sun. This method is the most direct and reliable, but it is limited to stars within a few hundred light-years. It was the tool that allowed us to calibrate the next rung. The second rung was Henrietta Leavitt's Cepheid variables. As we discussed, these pulsating stars are the key to measuring distances across the visible galaxy and to other nearby galaxies. But even Cepheids have their limits. They are bright, but they are not bright enough to be seen across the vast distances of the entire dark matter halo. To measure the full extent of the dark matter halo, astronomers had to invent a new, more powerful rung on the ladder: dynamical mass measurement. This technique is the core of how we weigh the invisible. The principle is simple, rooted in the laws of Newtonian gravity. The speed at which an object orbits a central mass is directly related to the amount of mass contained within that orbit. This is the same principle that allows us to calculate the mass of the Sun by observing the Earth's orbital speed. To measure the dark matter halo, astronomers look for tracer objects, stars, globular clusters, or satellite galaxies that are orbiting the Milky Way at extreme distances. By measuring the velocity of these tracers and knowing their distance from the galactic center, they can calculate the total mass of the Milky Way's gravitational well out to that point. The key insight is that the mass calculated from the orbital speed of the tracers is far greater than the mass of all the visible matter, stars, gas, dust, within that radius. The difference is the mass of the dark matter halo. One of the most effective tracers is the velocity dispersion of the Milky Way's satellite galaxies. These small, faint galaxies, like the Large and Small Magellanic Clouds, are bound to the Milky Way's gravitational field. By measuring the range of their velocities, how fast they are moving toward or away from us, astronomers can infer the total mass of the Milky Way's halo. The most recent and precise measurements come from the Gaia Space Telescope. Gaia is not just mapping the positions of stars, it is mapping their three-dimensional velocities. This unprecedented dataset has allowed astronomers to track the motion of millions of stars in the stellar halo, including the remnants of devoured dwarf galaxies like the Gaia Enceladus/Sausage. By analyzing the orbits of these halo stars, astronomers can build a gravitational map of the Milky Way. They can see where the mass is concentrated, and they can see how far out the gravitational influence extends. The results consistently point to a dark matter halo that is not only massive but also vastly extended. The current consensus, based on these dynamical measurements, is that the Milky Way's dark matter halo extends to a radius of at least 200 kiloparsecs, about 650,000 light-years, and possibly up to 300 kiloparsecs, nearly a million light-years. This is the true colossal size of our galaxy, a size that is dictated by the invisible. But the story of the Milky Way's size is also a story of cosmic anomalies and unresolved mysteries. The dark matter halo, while a successful explanation for the galaxy's rotation curve, is not without its own puzzles. One of the most persistent puzzles is the cusp core problem. Cosmological simulations, which model the formation of galaxies in a universe dominated by cold dark matter, predict that the density of dark matter should peak sharply at the center of the galaxy, forming a cusp. However, observations of many dwarf galaxies and some recent studies of the Milky Way suggest that the dark matter distribution in the center is flatter, forming a core. This discrepancy is a major challenge to the standard model of dark matter. The leading explanation for the core is baryonic feedback. Baryonic refers to normal matter: stars, gas, dust. When massive stars in the galactic center explode as supernovae, they can drive powerful outflows of gas. These outflows can dynamically stir the dark matter in the core, pushing it outward and flattening the central cusp into a core. This means that the visible matter, the stars and gas, are actively shaping the invisible dark matter halo. This interaction between the visible and the invisible is a key theme in the story of the Milky Way's size. The 100,000 light-year disk is not just passively sitting inside the dark matter halo, it is dynamically interacting with it, constantly reshaping its structure. Another profound mystery related to the dark matter halo is the missing satellites problem. Simulations predict that the Milky Way's dark matter halo should be teeming with thousands of small, dark matter subhalos, each a potential host for a dwarf galaxy. However, astronomers have only observed about 60 satellite galaxies orbiting the Milky Way. Where are the rest? There are two main possibilities. The first is that the missing subhalos are simply too small and faint to be detected. They may contain only a few stars, or no stars at all, making them truly dark subhalos. The second possibility is that the standard model of cold dark matter is slightly wrong, and that a different type of dark matter, such as warm dark matter, would naturally suppress the formation of the smallest subhalos. The search for these missing satellites is one of the most active areas of research in astronomy. Every new discovery of an ultra-faint dwarf galaxy, a galaxy with a mass dominated by dark matter, helps to map the structure of the dark matter halo and refine our understanding of the Milky Way's true size. The most extreme examples of these dark matter-dominated galaxies are the ultra-faint dwarf galaxies. These are the smallest, dimmest galaxies known, often containing only a few thousand stars. But their stars are moving so fast that they must be held together by a gravitational force far greater than their visible mass suggests. They are, in essence, tiny dark matter halos with a few stars sprinkled in. The discovery of these ultra-faint dwarfs, often found at the very edge of the Milky Way's gravitational influence, is a direct confirmation of the vast, extended nature of the dark matter halo. They are the outposts of our galaxy, the farthest reaches of its gravitational domain. The size of the Milky Way, therefore, is not just a measure of its physical extent, it is a measure of its gravitational reach, a reach that extends far beyond the visible light and into the realm of the invisible. But the story of the Milky Way's size is also a story of cosmic motion. The galaxy is not a static object. It is a colossal, spinning, and moving structure. The Milky Way's disk rotates at a speed of about 220 kilometers per second at the Sun's location. At this speed, it takes our solar system about 240 million years to complete one full orbit around the galactic center. This period is known as a cosmic year. The last time the Sun was in its current position, the Earth was in the Triassic period, and the dinosaurs were just beginning to emerge. This rotation is the most direct evidence for the dark matter halo. Without the extra gravitational pull of the dark matter, the stars on the outer edge of the disk would be moving too slowly to stay in orbit, and the galaxy would have long since dispersed. But the Milky Way is also moving through the universe. As we discussed, the entire local group is being pulled toward the great attractor at a speed of hundreds of kilometers per second. This motion is a direct consequence of the inhomogeneity of the cosmic web. The universe, while uniform on the largest scales, is lumpy on the scale of superclusters. The denser regions, like the great attractor, exert a stronger gravitational pull, causing the surrounding galaxies to flow toward them. This motion is a profound reminder that the Milky Way, despite its colossal size, is not an isolated island. It is a single component in a vast, interconnected cosmic machine. Its size and mass are defined not just by its internal structure, but by its gravitational relationship with the rest of the universe. The most recent and mind-bending discovery related to the Milky Way's motion is the possibility that we are traveling through a cosmic void. The KBC void, the immense empty region of space, is not just a passive backdrop. It is actively influencing our motion. The fact that we are on the edge of this void means that the gravitational pull on one side of the Milky Way is weaker than the pull on the other side. This gravitational imbalance contributes to the overall flow of the local group, pushing us toward the denser regions of the Laniakea supercluster. The size of the Milky Way, therefore, is a concept that must be understood in 4 dimensions, not just its spatial extent, but its motion through time. The galaxy is constantly growing, constantly moving, and constantly being reshaped by the gravitational forces of the cosmos. The final, definitive answer to the question, how big is the Milky Way, is a number that is constantly changing. It is a dynamic, evolving boundary that is being pushed outward by the accretion of new matter and pulled inward by the gravitational tension with its neighbors. But the most important takeaway is the profound shift in perspective that this knowledge provides. We have moved from the cozy, Earth-centered universe of Ptolemy to the colossal, dark, matter-dominated galaxy of the 21st century. The Milky Way is not just a collection of stars, it is a gravitational behemoth, a structure whose true size is defined by the invisible. and the journey to understand this invisible giant is the ultimate testament to human curiosity and ingenuity. To truly grasp the scale of the Milky Way, we must journey to its absolute core, the gravitational anchor that dictates the motion of every star within its million light-year reach. This is the realm of extreme physics, a place where the laws of nature are pushed to their breaking point, the galactic center. The center of the Milky Way, located 27,000 light-years away in the direction of Sagittarius, is a region of such intense density and energy that it is almost impossible to observe in visible light. The intervening dust and gas, the same cosmic soot that fooled Herschel, completely obscures our view. To penetrate this veil, astronomers must use radio waves and infrared light, wavelengths that can pass through the dust clouds unimpeded. What they have found is a region of staggering complexity, a cosmic metropolis anchored by the supermassive black hole, Sagittarius A. SGR-A is not just a massive object, it is the gravitational heart of the galaxy. Its 4 million solar masses create a gravitational well so deep that it warps the fabric of space-time for thousands of light-years around it. The immediate vicinity of Sagittarius A is a chaotic, violent place. Stars orbit the black hole at incredible speeds, some completing a full revolution in mere years. The star S2, which we mentioned earlier, is the most famous example, a cosmic speedster whose orbit confirmed the black hole's existence. But the black hole is not the only feature of the galactic center. Surrounding it is a dense nuclear star cluster, a region packed with millions of stars, many of them young, massive, and blue. These stars are born in a turbulent environment, constantly being buffeted by the black hole's gravity and the intense radiation from their neighbors. The most striking feature of the galactic center is the central molecular zone, CMZ, a massive ring of dense molecular gas that orbits SGR-A at a distance of about 100 light-years. This ring is the star-forming engine of the galactic core, a region of intense compression and turbulence that is constantly giving birth to new stars. The energy output from the galactic center is immense. Powerful outflows of gas and radiation, driven by the black hole and the massive stars, stream out of the galactic plane, creating two colossal, hourglass-shaped structures known as the Fermi bubbles. These bubbles, discovered in 2010, extend for 25,000 light-years above and below the galactic plane. They are a testament to the past activity of SGR-A. While the black hole is relatively quiet today, these bubbles are the fossil record of a time when it was actively feeding, consuming gas and stars and unleashing a torrent of energy into the galaxy. The existence of the Fermi bubbles is a crucial part of the Milky Way's size story. They show that the galaxy's influence extends far beyond the visible disk, pushing gas and energy into the stellar halo and the dark matter halo. They are a visible manifestation of the galactic wind, a force that is constantly shaping the galaxy's environment. The size of the Milky Way, therefore, is not just a measure of its mass, it is a measure of its energy output. The black hole at the center, the ultimate anchor of the galaxy, is also the source of the most powerful forces that shape its structure. But the most profound implication of the Milky Way's colossal size is the nature of dark matter itself. If 95% of the mass that defines our home is invisible, then our understanding of the universe is fundamentally incomplete. The search for the dark matter particle is one of the most intense and expensive scientific endeavors in history. The leading candidate is the WIMP, a hypothetical particle that interacts with normal matter only through gravity and the weak nuclear force. Experiments around the world, such as the XENONNT and LUXZEPLIN detectors, are buried deep underground, shielded from cosmic rays, in an attempt to detect the faint, rare interactions of WIMPs with normal matter. These detectors are essentially massive tanks of super pure liquid noble gases, waiting for a dark matter particle to collide with an atomic nucleus and create a tiny flash of light. The dark matter halo of the Milky Way is the laboratory for these experiments. As the Earth orbits the Sun, and the Sun orbits the galactic center, we are constantly moving through the dark matter halo. This means that a stream of dark matter particles is constantly flowing through the Earth, through our bodies, and through the detectors. The size of the Milky Way, therefore, is directly related to the density of dark matter in our local neighborhood. The more massive and extended the halo, the more dark matter particles are expected to be flowing through the solar system. The search for dark matter is not just a search for a particle, it is a search for a new physics. If WIMPs are not the answer, then the dark matter could be something even more exotic, such as axions, hypothetical particles that are much lighter than WIMPs, or even primordial black holes that formed in the very early universe. The size of the Milky Way, defined by its dark matter halo, is a constant reminder of this cosmic ignorance. We live in a galaxy whose true nature is hidden from us, a galaxy that is dominated by a substance we cannot see, touch, or directly measure. But the story of the Milky Way's size is also a story of cosmic ecology. The galaxy is not just a collection of stars, it is a living system, constantly recycling matter and energy. The interstellar medium, the gas and dust that fills the space between the stars, is the raw material for star formation. This gas is constantly being enriched by the supernovae of massive stars, which explode and scatter heavy elements, the building blocks of planets and life, into the galaxy. The Milky Way is a cosmic foundry, constantly forging new elements and new stars. The spiral arms are the nurseries of this process, the regions where the density waves compress the gas and trigger star formation. The size of the Milky Way, therefore, is a measure of its capacity for life. The vast, extended dark matter halo provides the gravitational stability that allows the disk to remain thin and relatively undisturbed, a crucial factor for the long-term survival of planetary systems. If the Milky Way were a smaller, less massive galaxy, it would be more susceptible to mergers and gravitational perturbations, which could disrupt the delicate orbits of stars and planets. The colossal size of the dark matter halo is the cosmic shield that protects the visible disk. The story of the Milky Way's size is a journey from the visible to the invisible, from the local to the cosmic. It is a story that began with a faint smudge of light in the night sky and has culminated in the realization that our home is a gravitational behemoth, a structure over 1 million light years across, defined by a mysterious, invisible substance. The final, profound implication of this colossal size is the philosophical shift it demands. We are not at the center of the universe, or even the center of our own galaxy. We are a tiny, luminous speck in the suburbs of a dark, gravitational giant. This realization is not a demotion, it is an elevation. It is a testament to the power of human reason, the ability to overcome the limitations of our senses and to map a universe that is far vaster, stranger, and more beautiful than we could ever have imagined. The Milky Way is our home, a colossal, dynamic, and mysterious structure. And the journey to understand its true size is the journey to understand our true place in the cosmos. The ultimate frontier of the Milky Way is not a wall of stars or a sudden drop-off in density. It is a gravitational horizon, the point where the pull of our galaxy is finally overwhelmed by the pull of the surrounding universe. This is the galactic edge, and it is the final, most elusive boundary in our quest to measure the Milky Way's true size. To find this edge, astronomers must look for the most distant objects that are still gravitationally bound to the Milky Way. These are the cosmic sentinels, the farthest outposts of our galactic empire. One of the most powerful tools for finding these sentinels is the study of hypervelocity stars, HHVS. These are stars that are traveling at such extreme speeds, hundreds of kilometers per second, that they are on a trajectory to escape the Milky Way's gravitational pull entirely. These stars are thought to be ejected from the galactic center by the supermassive black hole, Sagittarius A. When a binary star system wanders too close to the black hole, one star is captured and the other is violently flung out of the galaxy at immense speed. By tracking the trajectories of these escaping stars, astronomers can measure the escape velocity of the Milky Way at different distances. The escape velocity is the speed required to break free from the galaxy's gravity. By finding the point where the escape velocity drops to zero, they can infer the gravitational boundary of the dark matter halo. The most distant HVSs found so far are located at distances of over 300,000 light-years from the galactic center. The fact that these stars are still moving at high speeds but are on the verge of escaping confirms the immense gravitational reach of the dark matter halo. They are the cosmic cannonballs that are testing the limits of our galaxy's size. Another crucial sentinel is the Oort cloud, the hypothetical spherical cloud of icy bodies that is thought to be the source of long-period comets. The Oort cloud is believed to extend out to a distance of about 100,000 astronomical units, AU, or about 1.5 light-years from the Sun. This is the boundary of the solar system, but it is still a tiny fraction of the Milky Way's size. However, the outer edge of the Oort cloud is constantly being perturbed by the tidal forces of the Milky Way's disk and the gravitational influence of nearby stars. The Oort cloud is the first layer of the galactic environment, the point where the Sun's gravitational influence begins to give way to the galaxies. The true galactic frontier, however, is defined by the most distant globular clusters and satellite galaxies. These are the objects that are still orbiting the Milky Way, but are on the very edge of its gravitational well. One of the most distant globular clusters, Palomar 5, is located about 60,000 light-years from the galactic center. It is a diffuse, ancient cluster that is currently being torn apart by the Milky Way's tidal forces, leaving behind a long, faint, stellar stream that stretches for thousands of light-years. This stream is a visible marker of the galaxy's gravitational reach. The most distant satellite galaxies, such as the Leo once dwarf galaxy, are located at distances of over 800,000 light-years from the galactic center. The fact that these galaxies are still bound to the Milky Way, despite their immense distance, is the most powerful evidence for the colossal size and mass of the dark matter halo. They are the gravitational anchors that define the Milky Way's true boundary. The final, most profound realization is that the Milky Way's size is not a fixed number, but a probabilistic boundary. The dark matter halo is not a solid sphere. It is a diffuse cloud that gradually fades into the intergalactic medium. The edge is the point where the probability of a particle being bound to the Milky Way is equal to the probability of it being bound to the surrounding cosmic web. This probabilistic boundary, based on the latest dynamical models, places the Milky Way's true diameter at around 2 million light-years. This is the final, mind-bending answer to our question. The Milky Way is a gravitational leviathan, a structure so vast that the light from its center takes over 1 million years to reach its edge. It is a home that is defined by its invisibility, a colossal, dark matter-dominated giant that is constantly moving, constantly growing, and constantly being reshaped by the forces of the cosmos. We finally know how big the Milky Way is, not because we have seen its edge, but because we have learned to read the invisible language of gravity. We have mapped the ghost in the machine, and in doing so, we have redefined our place in the universe. The journey to understand the cosmos is the journey to understand ourselves, and the colossal size of our galactic home is the ultimate testament to the vastness of the universe and the power of human curiosity. The final words of this epic journey must bring us back to the profound realization of our own scale. We began by looking up, and we must end by looking inward, armed with the knowledge of our colossal home. The Milky Way, a structure of 2 million light-years in diameter, is the stage for our existence. Every star, every planet, every moment of human history has unfolded within the gravitational embrace of this dark matter giant. The light that left the most distant globular clusters, the light that is currently tracing the streams of devoured dwarf galaxies, has been traveling for hundreds of thousands of years to reach our telescopes. When we look at the edge of the Milky Way, we are looking deep into cosmic time, witnessing the galaxy as it was in the distant past. The story of the Milky Way's size is the story of cosmic evolution. It is the story of a galaxy that began as a small, turbulent cloud of gas and dark matter, and grew into a colossal, spiral behemoth through a relentless process of accretion and merger. The next chapter in this story, the collision with Andromeda, is not an ending, but a transformation. It is the final, grand act of galactic evolution, a merger that will create a new, even larger home for our descendants. The ultimate size of the Milky Way is a cosmic truth that humbles and inspires. It is a reminder that we are part of something unimaginably vast, a single, luminous speck in a dark, gravitational ocean. But it is also a reminder that the human mind, armed with curiosity and ingenuity, can transcend the limitations of its physical location. We are trapped inside the Milky Way, but we have mapped its boundaries, weighed its invisible mass, and predicted its future. We finally know how big the Milky Way is, and the answer is not just a number, it is a new cosmic perspective. It is the realization that our home is a dark, colossal giant, and that the greatest discoveries are often found not in the light, but in the invisible. Thank you for joining us on this journey into the depths of the cosmos. Until next time, keep looking up and keep questioning the scale of your universe.